So today we are going to talk about decimal multiplication, and I want to start by making sure we understand what each one of our base 10 models is going to represent. So in grades 1 through 3, this flat represented 100, and in 4th grade students learned that this could represent one whole, with each column being 1/10 and each individual square being 100th. So for our models today, this will represent one whole, which makes this 1/10 because it is 1/10 of the size of the whole. It takes 10 of these to make up one whole. And this will represent 100th because it takes 100 of these to make up one whole. So those are the models that we'll be using. The first problem that I want us to look at together is 42 hundredths times 2. So when I say 42 hundredths times 2, I mean two groups of 42 hundredths in each one. So here's 42 hundredths, and here's another set of 42 hundredths. So in my model, I have one group of 42 hundredths, another group of 42 hundredths. I would ask kids to prove to me how I know that's 42 hundredths. And they would say this is 1/10 or 10 hundredths, 2/10 or 20 hundredths, 3/10 or 30 hundredths, 4/10 or 40 hundredths, 41 hundredths, 42 hundredths. So we need to make sure they know how to count with these. So this is one group of 42 hundredths, and this is two groups of 42 hundredths. So if I wanted to know the product of 2 times 42 hundredths, I could group the tenths and then group the hundredths, and I could say this is 1, 2, 3, 4, 5, 6, 7, 8 tenths and 4 hundredths, or 84 hundredths. Now, I would want kids to be able to tell me, when I look at this model, what are the two factors? The two factors are 42 hundredths times 2. Two groups of 42 hundredths, or 2 times 42 hundredths. The two factors are 2 and 42 hundredths. You may have some children say that the two factors are 42 hundredths and 42 hundredths. But 42 hundredths times 42 hundredths is not the same as 2 times 42 hundredths. So we need to make sure that they remember that factors are the two numbers being multiplied together. Two equal groups times 42 hundredths in each group equals the product of 84 hundredths. So when we model these on a pictorial model, we use a blank hundreds chart, a 10 by 10 that matches our flat, so that students can see this represents one whole. So if I'm going to model two groups of 42 hundredths, I'm going to start by shading in 42 hundredths. So, and I would have them talk me through this. This is 1/10, and we would shade in all the way over. We want 42 hundredths. And I would say, right now we have 4/10. What's another way to name that? 40 hundredths. We need 42 hundredths, so I'm going to shade two more. Now, I need another set of 42 hundredths. Sometimes kids want to start with their 42 hundredths over here and make 1, 2, 3, 4 and shade in two more. Or they might want to just start right here and do 1, 2, 3, 4/10 and two more. But we want our model, if it's a true representation of two groups of 42 hundredths, or 2 times 42 hundredths, it needs to represent both factors and the product. So in order to represent the product, all of the cubes, or all of the boxes that I shade in, need to be sequential. I need to start right here where I left off and shade in another set of 42 hundredths. So I would have them count with me. This would be 8 hundredths. I'm not to 42 yet. I'm going to shade in a column of 10. Now I'm at 18 hundredths. Now I'm at 28 hundredths. Now I'm at 38 hundredths, 39 hundredths, 40 hundredths, 41, 42 hundredths. I've shaded in 2 groups of 42 hundredths. Now I want kids to label, label, label. So I'm going to have them draw some markings so they can see where the 2 groups of 42 hundredths are. And I'm going to be a little bit dark here so they can see where those 2 groups are. And I want them to label this. This is 42 hundredths and this is 42 hundredths. And the product is 84 hundredths. So I want them to recognize factor times another factor equals a product. 2 times 42 hundredths is the same as 2 groups of 42 hundredths, and that equals 84 hundredths. I can see that in my model. There are 2 equal groups here. Both of these groups have 42 hundredths in it, and there's a total of 84 hundredths shaded. So let's look at the next one. For the next one, we are going to do 3 groups of 5/10. Now, if I model that with base 10 blocks, this would be 1 group of 5/10. 1, 2, 3, 4, 5, and each one of these represents a tenth. Here's 2 groups of 5/10, and here's 3 groups of 5/10. So I can see I have 3 equal groups. Each one of them has 5/10 in it. And I want to be able to say, what's the product of 3 times 5/10? Well, I know it takes 10/10 to make 1 whole. And I can prove that by matching these up and saying, these 2 are the same size. This is 1 whole. 10/10 is equal to 1 whole. It's the same size. So I've got 1 whole and 5/10 more. Now, how can I help kids relate to this? 5/10 is the same as 2 quarters if they think about money. It's the same as 50 cents. So I know that if I have 50 cents and another set of 50 cents, I have 1 whole dollar. And then my third group of 50 cents would give me $1.50, or 1 and 5/10, which would give me my product. Remember, 3 groups, all equal. 3 groups of 5/10 is 1 whole and 5/10. So now what would that look like on a model? So I want to be able to see all of my groups. So I need 3 groups of 5/10. So I'm going to shade in 1 group of 5/10, 2, 3, 4, 5/10. I'm changing colors now because I want to be able to tell the individual groups. Here's 2 groups of 5/10. I can shade in the rest of this because it takes another set of 5/10 to make a whole. So there's 2 groups of 5/10, but I need 3 groups. So I'm going back to my other color. 1 more group of 5/10. 1, 2, 3, 4, 5/10. And I'm going to label it. I'm going to draw my lines so I can see my equal groups. This is 5/10, this is 5/10, and this is 5/10. So 3 groups of 5/10 equals 1 and 5/10. And I can also write that as 3 times 5/10 equals 1 and 5/10. Let's do one more of these where both of our factors are greater than 1 whole. And we are going to model 1 and 2/10 times 2. So here's 1 and 2/10, and I want 2 groups of 1 and 2/10. So here is another group of 1 and 2/10. So I have 1 group of 1 and 2/10. I have 2 groups of 1 and 2/10. To find my product, I would group the place value blocks that are the same. 2 wholes and 4/10 is my product. My factors are 1 and 2/10 times 2 because there are 2 equal groups of 1 and 2/10. My product is 2 and 4/10. Now I would ask kids, when I get ready to model this, do you think I will need 1, 2, or 3 holes to be able to draw my model? And see what they say. we know we're modeling 2 times 1 2/10, or 2 groups of 1 2/10. So I would want them to predict how many blocks do we need. And I should hear some thinking like, well, I know I would need more than 2 whole blocks because when we modeled it, we had 2 wholes and then some more. So I need all 3 of these. And I would say to them, will I use all of the third one, part of the third one, more than half of the third one, less than half of the third one? Get their thinking going. I know I had 4/10 left over after I had these 2 holes. So I know I'm going to have 4/10 of this model shaded in. Is that more than half of that model or less than half of that model? I know it's less than half of that model because half of it is 5/10. So let's model it. I'm going to show our 2 factors, 2 groups of 1 2/10. I'm going to need 2 colors. I'm going to start by shading in 1 2/10. So I'm going to shade this whole box. One whole grid represents 1 whole. I need 2/10 of the next grid because my groups are 1 2/10. So here's 1 2/10. Now, here's where kids want to try to figure out a different way to do it, and they might want to start by shading in the whole because they know they're going to use this whole, and then coming over here and shading part of this. But we're going to remind them that we want our model to show both factors and the product. So I have to start from right here and shade another 1 2/10. So let's talk about what kids might do with that. So I might shade in the rest of this and then shade in 2/10 over here and think I'm done. And why might kids think I'm done? Because we completed another 1 2/10. But have we shaded in? Was this a whole? It wasn't. This was only 2, 3, 4, 5, 6, 7, 8/10. And I need 1 2/10, which is the same as 12/10. So right now I've shaded in 10/10 or 1 whole. I still need to shade in these 2/10. So I have to keep going. I can prove that with my model because we said our product was 1 whole, 2 wholes, and 4/10. 1, 2, here's my 2 holes, 4/10, here's my 4/10. So then I want them to label it. I'm going to draw my line here, and I'm going to label this is 1 2/10, and this is 1 2/10. I can see 2 equal groups, each being 1 2/10. My product is 2 holes and 4/10. 2 times 1 2/10 is 2 4/10. So now we're going to switch gears and we're going to talk about how we model when we are looking at 2 decimals that are both less than 1 whole. Now we have to keep in mind the limits of our TEAC. Our TEAC says products to the hundredths. So I never want to do anything that gives me a product with more than 2 decimal places. In 5th grade, we are limited by 2 decimal places. So that means I can do problems like we were just doing, where I multiply a whole number times a number with hundredths, like the very first problem that we did, because my product is now in the hundredths place. So I can't do anything bigger than this, or more decimal places than this. Or I can multiply a number that has tenths times a number that has tenths, because that will give me a product of the hundredths. Or I could multiply a whole number times a number that has tenths, because that's less than products to the hundredths place. It would be products to the tenths place. So we have to make sure all of our problems have no more than 2 decimal places in the product. We can't push past that. That's what our TEAC says we teach. And because we're introducing this brand new skill, we are going to stay in our lane and make sure we are teaching our TEAC. So for this first problem, we are going to model 4/10 times 6/10. And we're going to start out doing that with place value blocks. We start everything new with concrete. So I've already built 4/10, but I built it as hundredths. So I need kids to build these as hundredths, not just say, here's 4/10, Miss Cooper, I'm ready. I can't take part of this. I can't take 6/10 of this. I could take a fourth of it or 2/4. I could take half of it, but I can't take tenths because I don't have 10 pieces. I don't have 10 equal groups to be able to take tenths of this. So I want kids to understand that there are two different kinds of decimal multiplication that we look at in 5th grade. We look at equal groups, which is the first kind we modeled, where we have 2 groups of some number or 4 groups of some number. And then we also look at decimal multiplication where we only want part of whatever we're multiplying. So in this case, I have 4/10 and I want part of that. I don't want all of it. I don't want equal groups of it. I want 6/10 of it. And if I want 6/10 of it, well, I have to start by knowing what 1/10 of it is. So I want kids to model this by spreading these out into 10 equal groups. So all I've done is take our model, 4/10, and break it into 10 rows. Because if I want to take 6/10 of something, I need to be able to see 10 equal groups. And right now I have 10 equal groups. I want 6 of those tenths. This is 1/10, 2/10, 3/10, 4/10, 5/10, 6/10, 7/10, 8/10, 9/10, 10/10 of the whole model. My whole model is 4/10. 1, 2, 3, 4. I want 6/10 of that. So here's 1/10, which would be 4/100. There are 4/100 that make up this 1/10. This tenth is another 400. So if 1/10 is 4/100, 2/10 is 8/100. 3/10 is 12/100. 4/10 is 16/100. 5/10 is 20/100 or 2/10. And 6/10 is 24/100. I can say that there are 1, 2, 3, 4, 5, 6 tenths because there are 10 equal groups and this is 6 of those 10 groups. And then I'm not using these. I don't want all of it, remember? I only want 6/10 of it. So this is where we come up against that thinking in 5th grade that kids have this idea that multiplication always gives you a bigger answer. And we disprove that in 5th grade. So I would have that conversation with them. When does multiplication give us a bigger answer? When is our product bigger than our factors? In this case, our product is smaller than our factors because remember, I don't want all of this 4/10. I only want part of it. So let's look at how we would model that on paper. So I would start by shading in the number that I started with. I started by building 4/10, and I'm going to shade in 4/10. That's what I started with. But remember, I don't want all of this 4/10. I only want part of it. So I'm going to shade the other way to represent these rows that we have here. So this would be, and I'm going to shade all the way across, this would be 1/10, this would be 2/10, 3/10, 4/10, 5/10, 6/10. And I want to label it, and then I want you to see where the answer is. So remember, this part is our 6/10. This is our 6/10. And this part down here at the bottom, this is our 4/10. Where they overlap, look what happens right here where the two colors overlap. I've taken 6/10 of this whole, and inside here is 24/100. It's a 4 by 6 array, and each piece is 100th. So 4 by 6 is 24, and each one of these is 100th, 24/100. So we can see that this equals 24/100. So let's do another one. So for this problem, we're going to model 3/10 times 8/10. And I would ask kids ahead of time, can you predict, is my answer, my product, going to be bigger or smaller than my factors? When I multiply something by a number less than one whole, my answer or my product gets smaller because I only want part of this 3/10. Now I want to make sure kids believe me or agree that this is 3/10. So if I looked at this, I could see that I have 3/10 here. I could prove it by saying this is equal to 3/10. It's the same thing. I could stack them up, try to not knock them over, and prove that this is 3/10. That's what I'm starting with. But I can't break this into very many different groups. I could break it into thirds. I could say you get a third, I get a third, you get a third. But that's not what our problem says. Our problem says we want 8/10 of it. So I need to use a model that I can break into tenths. And this model happens to give me that option because there are 10 rows, because this is 3 by 10. So in order for me to show 8/10 of it, I have to start by knowing what 1/10 of it is. So I'm going to separate these out like we did on the previous problem so that I can see the 10 rows. And then we can talk about where the factors are and where the product is. So I want 8/10 of this model. There are 10 parts. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So each part is 1/10 of the model. So 1/10 of this model is 3/100. 2/10 of this model is 6/100. 3/10 of this model is 9/100. 4/10 of this model is 12/100. 5/10 of this model is 15/100. 6/10 of this model is 18/100. 7/10 of this model is 21/100. 8/10 of this model is 24/100. 9/10 of this model is 27/100. And 10/10 of this model is the whole thing, or 30/100, also equal to 3/10, which is what we started with. In our problem, we want 8/10 of it. So we want 1, 2, 3, 4, 5, 6, 7, 8/10 of it. And I'll put this here just to be able to separate. This is the part of this that we want. We want 8/10 of it. We don't want the rest of this model. We just want this part. So I can see 3/10 times 8/10 is equal to 24/100. If I counted these up, it would be a 3 by 8 array, and each of these represents 1/100. So 3 times 8 is 24. Each one represents 100, so it's 24/100. So now let's model it on our paper. So we are going to start by modeling the 3/10. So here's 1, 2, 3/10. And then with my other color, I'm going across my model and I'm going to shade 8/10. I want to be able to see both colors because remember, my goal is to be able to see both factors and the product. That's 5, 6, 7, 8. Now let's label. Here's my 3/10. Here's my 8/10. And where they overlap is my 3 by 8 array, 3 by 8 array, and each one of these represents 100. So a 3 by 8 array is 24, and they are all hundreds, so this is 24/100. I didn't really mean to pick two problems with the same product, but that could blow some kids' minds, so that might be a great conversation to have, that there's more than one way to equal 24/100. Okay, let's do one more. We're going to push all this back together, so we want to prove it every time. And this time we're going to solve 2/10 times 5/10. So here's my 2/10. If kids don't believe me, I can separate them and show them. This is 1/10, and this is 1/10. In this problem, I want to solve the model 2/10 times 5/10. Now, in this case, I can't multiply by 5/10. I want kids to recognize, what's 5/10 equal to? It's equal to 1/2. Could I take these and say, I have 2 of these. Can you show me what half is equal to? Well, if I have 2, half is equal to 1. So in this case, I could use these and say half of this model, this is half of it, and this is half of it. So I should know right now my answer should be 1/10. 2/10 times 1/2 is 1/10 because I'm taking 1/2 of it. Let's prove it with the way we've been solving these problems. So I'm going to push these back together because I want to push it into 10 equal groups so I can find 5/10. So there's our 10 groups. Let's count it like we've been doing. 1/10 of this model is 2/100. 2/10 of this model is 4/100. 3/10 of this model is 6/100. 4/10 is 8/100. 5/10, that's what we're looking for. 5/10 is 10/100 or 1/10, which is what we just proved with this. 2/10 times 5/10 or 1/2. Half of this is 1/10. We just counted and proved that when I get to 5/10, I'm at 10/100, which is equal to 1/10. So 5/10 of it is here. Here's the other 5/10. I don't want this 5/10. I just want 5/10 of the model. So now let's shade it in and prove it. So here's my 1/10, my 2/10. I only have 2/10 this time, and I want 5/10 of this model. So I'm going to shade in 1/10, 2/10, 3/10, 4/10, 5/10, and then I'm labeling everything. Here's my 2/10 down here, and here's my 5/10 here. I box in where they overlap. It is a 2 by 5 array. 2 times 5 is 10, and each one of these represents 1/100th, so it's 10/100ths or 1/10. So some big takeaways. We always start with concrete. We model every single thing we do. We model it, then we draw it on paper. We definitely have to teach the standard algorithm, but here's the thing. Once they get to this point of understanding it, the standard algorithm will make a lot more sense to them. They'll understand why the decimal place goes where it goes because they've counted it, they've seen it, they've built it, they've counted it on a model. They'll understand instead of just following a procedure that says count the number of decimal places in each factor and then total that up and put that many decimal places in your product. They'll also understand why we don't just bring the decimal straight down. If I think about this problem and I had written it in a standard algorithm with 4/10 times 6/10 under it, kids would say 4 times 6 is 24. The most common mistake is to bring the decimal straight down. That would mean the answer is 2 and 4/10, but we've proven now, both by building it and by drawing it, that the answer is not 2 and 4/10. That would be all of this one, and 4/10 of the next one. And we only want part of this. We didn't even start with one whole. How can we take part of it and end up with more than 2 wholes? So we're building the foundational understanding so that when they get to the abstract of following an algorithm, it makes sense. So concrete, then pictorial, then we can move to the abstract standard algorithm. Please let me know if you have any questions. Practice this, watch the video, rewind it, watch it again. Do the problems with me while you're watching it. Solve each of these problems with me. And then I would really recommend you just use these exact problems with your kids because you will have already practiced them. You will know how to model them, you will know how to explain them, and you'll be able to do that with your students.